Okay, so let's begin a new topic today, and that is let us try and see if we can calculate the what are known as the specific heats of various gases. So, specifically I have in mind gases such as ideal gas and quantum Fermi gas and quantum Bose gas. So, let us start with ideal classical gas. So, well, regardless of which type of gas it is, I can define the specific heat at constant volume as the rate of change of the internal energy of the system versus temperature. So, it is the slope of the internal energy plotted versus temperature. When you fix the density of particles is fixed and also the number of particles is fixed. So, the volume and the number of particles are assumed to be fixed, and you change the internal energy. So, in other words, you know that basically what I have in mind is a system that is in contact with a reservoir. So, they come to a thermal equilibrium at the common temperature, and what I have for the system is that the system does not have really a well defined internal energy, but it certainly has a well defined most probable value of the internal energy. So, henceforth when I speak of internal energy of a system at constant temperature, I obviously mean that most probable value. Okay. So, I have already told you that the most probable value is overwhelmingly likely in a system that is thermodynamically large. So, it is in the thermodynamic limit, the most probable value is more or less the only possible value. The other values are incredibly less probable. So, given this state of affairs, the total internal energy, the most probable value of the total internal energy is going to change if I decide to change the common temperature of the system and its surroundings. So, the idea is that the specific heat is basically defined as the change in that most probable value of the internal energy and the ratio of that with the change in the temperature of the surroundings and therefore of the system. So, that is called the specific heat at constant volume, because you are fixing the volume and of course, the number of particles. We are going to assume that is anyway fixed, but the volume is fixed, so that the system does not have flexible walls. So, that would correspond to specific heat at constant volume. Okay. So, that is what I have written here in this sentence. So, the specific heat at constant pressure by contrast is defined differently, because then you have to take into account the fact that the walls of the container move around, and therefore, some additional energies are involved. So, instead of the internal energy, the analog of the internal energy in the case of constant pressure is what is known as enthalpy, and enthalpy is defined as U plus PV. So, in fact, it is instructive to understand why these definitions are the way they are. So, if you recall, the Helmholtz free energy in case of systems that have constant volume and constant number of particles, but variable energy was defined in this fashion. So, we defined it as the internal energy minus T s. So, this is basically telling you something interesting physically. So, what it is telling you is that the free energy that is available to you to do work is not the entire internal energy of the system, but less than this, less by this amount called T s. So, T s is the amount of energy that it's kind of gets wasted in terms of entropy. So, in other words, it's some kind of random energy that you can't really make use of, that's always present in the system, that you can never make use of. So, the energy that you can eventually make use of is the free energy, which is the total energy in the system minus the random energy which you cannot make use of. So, which is why we end up defining specific heat as the rate of change of internal energy with temperature, which is the quantity that is sitting here. So, similarly, in the case of systems at constant pressure, so if you recall that was actually defined in a similar way, that instead of internal energy there was enthalpy sitting here. So, similarly, the role played by the internal energy in the case of constant volume is taken up by enthalpy in the case of constant pressure. So, this would correspond to specific heat at constant pressure, and the rate of change of internal energy with respect to temperature is called specific heat at constant volume. So, now let us go ahead and see if I can evaluate these quantities for various gases. Let us start with a classical ideal gas. So, you know that in a classical ideal gas the total internal energy is 3 by 2 n kT, which we had just derived some time back, and as a result the specific heat at constant volume is just the rate of change of this with temperature, which is 3 by 2 n. Remember that I have put Boltzmann constant is 1 in all my lectures. So, as a result, but we also know, for instance, that the equation of state for a classical ideal gas is P v equals N T. So, if I add U plus P v, which is the definition of enthalpy, I get phi by 2 N T. So, now the rate of change of enthalpy with temperature is phi by 2 n. So, now if you take the difference between the two, I get something proportional to n, and of course, the uppercase C refers to the specific heat of the system as such, whereas the lowercase c refers to the specific heat of the system per particle. So, that is the only difference. So, for specific heat of the system per particle, the specific heat of the system per particle at constant pressure minus the specific heat of the system per particle at constant volume is 1 for a classical ideal gas only. Okay, so that was easy, and in fact, it is quite uninteresting as well, because everything is very simple. So, now let us get to something slightly more interesting, and that would correspond to quantum ideal gases. So, remember that when I speak of ideal gas, whether it is quantum or classical, I mean a gas where the constituent particles do not interact with each other, but rather only interact with the walls of the container maybe, or the surroundings or whatever. They do not interact amongst each other. But of course, in quantum mechanics that is a little bit hard to pin down, in the sense that, you know, if you talk about fermions, you know that you can't really put two fermions in the same state because of Pauli exclusion principle, and you could you know, raise your hand and say, well, that is a sort of an interaction as well. How can you ignore that? I mean, after all, it is an interaction in the sense that a fermion is sensing the presence of another fermion, and it is not allowing two fermions to occupy the same state. So, in that sense, it is true that there is some kind of an interaction. So, when we talk of ideal quantum gases, we of course mean something over and above that. So, these type of interactions which are due to fundamental laws of nature, which is regardless of the nature of the other forces involved. So, you know, such interactions that are always present, they are called statistical interactions. So, they are always present. So, for bosons there is a you know, also a statistical interaction caused by the fact that you can, you know, they are all indistinguishable, and you can put as many as you want in the same state. So, now let us get to quantum ideal gases, and if you recall, I had written down general expressions for the energy density, that is energy per unit volume, and the number density, which is the number per unit volume of quantum gases. So, if Q was plus 1, it corresponded to fermions, and Q was minus 1, it corresponded to bosons. So, now you could actually go ahead and perform this integration. So, you do not have to, you know, scratch your head about how to do this, because after all this is a very simple integral. You know, this R is you know, just a scalar quantity, and this implies a spherically symmetric integrand. So, I can always write the volume element as 4 pi r squared dr, and I integrate from r equal to 0 to r equal to infinity. That is what I would be doing here and there. Well, you can do it by hand, I mean you can try to do it by hand, but you will find that you will be stuck with a certain function that you won't be able to handle beyond a certain point, and so you will end up with a function which is what is known as a polylogarithmic function. So, polylog function. So, these are tabulated, and in fact, the definition of polylog function of z with the index s is defined in this fashion. So, this is polylog. So, we can tabulate these for various values of s. So, the values of interest in the case of 3-dimensional gases, quantum gases, is when s is 3 by 2 for density and when s is 5 by 2 for energy density. This for number density, we will have to calculate this polylog function for s equals 3/2, and for the energy density we need the polylog function for s equals 5/2. So, you do not have to get scared about these functions. I said, well, I do not know what they are, how would I learn the subject. Nowadays, there is no need to worry about all these. Nobody takes any pride in doing integrations anymore, because there are lots of symbolic algebra packages out there that do it for you. So, I have given such an example here in Mathematica, the language Mathematica. You can just use this as an example and just insert this command in the Mathematica language, and then out comes this answer. So, you do not have to worry too much about if you do not know how to do an integral. Nowadays, there is a lot of packages that do it for you. Okay, so, we can similarly write down the answer for pressure. So, the pressure also involves such an integral over these r's, and then this also involves the polylog function for 5 by 2. Okay, so, this was 5 by 2 as well. Now, that is interesting, because that is telling you something. So, regardless of whether what q is, I can so remember that if q was +1, it was fermions. So, if q was +1, it was fermions. If it was -1, it was bosons, and -1 q equals +1 was bosons, q equals -1, +1 was fermions, -1 was bosons. And I mean, let me be a little mischievous and say q equals 0. Well, that is strictly not allowed, because q was supposed to be plus or minus 1. So, let us try to become a little greedy and say, what does q equal to 0 correspond to? Well, that is certainly going to correspond to something which we are familiar with, because if this goes away, remember that if we ignored this q altogether, that corresponded to classical Boltzmann statistics or classical ideal gas, and that is what it is. So, it is classical ideal gas. So, I mean, so you can take one or the other point of view, namely you can either say that, well, in certain limits q can be ignored altogether, and therefore, only this survives, or alternatively I forcibly put q equal to 0, which is the same thing. So, now, so regardless of what that q is, you can see that if I take the ratio of the pressure which I have calculated in terms of this polylog function, which has an index 5 by 2, and the internal energy density, the energy density of the gas in terms of the same parameters. So, that also has index 5 by 2, and if I take the ratio, I get a whole bunch of constants, which then simplify to this incredibly simple fraction, which is 2/3. So, that is very interesting. But notice that this 2/3 should be not taken to be that universal. In fact, it is universal in the sense that it is applicable to Bose gas, Fermi gas, and classical ideal gas. However, it is only applicable if those gases live in 3 dimensions and the energy momentum dispersion is parabolic. So, that means I am talking about non-relativistic free particles. So, in other words, the E versus P is P squared by 2m, It's only then this works. And also I have to live in 3 spatial dimensions. So, I have to believe that the gases are existing in 3 spatial dimensions. So, if you have a situation where you can have for example, a metal where the conduction electrons can be modeled as a Fermi gas, a gas of fermions, and these days you can create a 2-dimensional conductor, which is basically you can think of the conduction channels of a MOSFET 2-dimensional or even 1-dimensional sometimes, depending upon the situation. So, you can have lower dimensional Fermi gases which are realizable in practice quite easily. And these days there is a subject called lattice. I mean, there is a subject where you trap, so it's called laser cooling or trapped atoms. So, you trap atoms in artificial lattices created by crisscrossed laser beams, and you can kind of coax those atoms to behave like ideal Bose gas or ideal Fermi gas, and nearly ideal Bose gas, nearly ideal Fermi gas. And you can test many of, so you can reduce the dimensionality by choosing your lattice to be deliberately 2-dimensional, and you can study various properties. So, so as a result, I am able to write down this really nice equation of state type of expression, which tells me that pressure times volume is 2/3 the internal energy. So, I do not have to in order to obtain equation of state, I do not have to redo any calculation. All I have to do is find the total internal energy, and that immediately gives me equation of state. Okay, so now, well, that was the absolutely correct answer without any further qualifications or comments, but it is also completely useless because I do not know what this function looks like or how it behaves. So, I can't really get any physical insight from this. So, in order to gain physical insight, I really have to make sure that I do not use these functions that I do not know how to deal with. So, it is better if I expand in a certain, in terms of a certain parameter that I choose to regard as being small, or I have to select a certain parameter which I feel is small, and then expand in powers of that and see how things behave as a result as a function of that parameter. So, that is called a controlled approximation, and we want to make such a controlled approximation. We want to expand in powers of something we can have a handle on, something we know we can control. So, one such approximation in this context is what is known as the Fugacity expansion, where if you recall, Fugacity is defined as e raised to beta times chemical potential. Given that beta and mu are real and beta is positive, so this means therefore that Z, which is the Fugacity, can never be negative, it is always real and positive. So, now so let us go ahead and try to see if we can evaluate an integral of this sort. So, remember that if n is 1, that would correspond to I would be calculating the density of particles when n is 0. So, when n is 1, I would be calculating the energy density, because if you go back here, so if this is r to the power 0 there, r to the power 0, and this is r to the power 2. So, that if I write it as r to the power 2n, so n is 0 corresponds to calculating density, and n equal to 1 actually corresponds to calculating energy density. This n equals 0 corresponds to calculating particle density, n equal to 1 corresponds to calculating energy density. Okay, so now let us go ahead and calculate this. So, I am going to start with fermions. So, for fermions, q is +1. So, now I can go ahead and expand in powers of z. Let us assume that z is really small compared to 1. So, in other words, z is positive and close to 0. So, in which case there is a well defined expansion that you can do, and clearly the leading term is proportional to z, because if you take the z upstairs, the leading term is going to V proportional to that, the next term is. So, you can just go ahead and evaluate this. So, you will have the answers in terms of the gamma function. So, if you remember the gamma of n minus 1, if n is integer, gamma of n minus 1 is just n factorial. When n is not integer, you will have to generalize this definition. So, I am going to assume you know how to do all this. If you do not, please look it up. Just go to any maths book that tells you how to define gamma function, and it will tell you how to generalize it to any complex number. Alright, so now given that I am able to write down this answer, this integral in terms of for fermions, in terms of an expansion, I can now go ahead and calculate the energy density and the number density. So, it comes out to be this expansion. For instance, if I take the ratio, that is interesting, because if I take this ratio energy density divided by number density, that is just the energy per particle. So, because you can, it is u by v divided by n by v. So, the v's cancel out and you get u by n. So, now the advantage of doing this is that a whole bunch of things cancel out as a result, and then you get this result. So, keep in mind that if you have a situation where you fix the number of particles. So, remember that this method actually is kind of, it tells you things that I do not want to know. For instance, it tells me, so the original formulas really tell me something which I do not care about that much. It tells me the energy density in terms of chemical potential. What is chemical potential? So, in chemical potential appears only when you have a system where the number of particles is not fixed. So, I am allowed to exchange the number of particles with my reservoir or surroundings, and what is fixed is the average number of particles. So, it is as if the number of particles is fluctuating. But remember that I have told you that in a thermodynamically large system, I can go back and forth between a description where the number of particles is truly fixed and the number of particles is fixed only in the sense of most probable value. And these I can go back and forth between these 2 points of view without paying any penalty, only if the systems are thermodynamically large, which means I am entitled to ignore fluctuations. So, I am going to always assume that that is the case, that I can ignore fluctuations, in which case, so conceptually they are equivalent. The conceptually studying a system that where the number of particles is truly fixed is equivalent to studying a system where the number of particles is fixed only on an average in the sense of most probable value. So, now that conceptually there is no problem, but then practically the problem is that I really have my, I want all my answers in terms of things that I can put my finger on, which is the number density of particles. I really do not know or do not care too much about what the chemical potential of my gas is. I just want to know that on an average I have these many particles in this volume, and can you tell me what is my energy density. So, so what this is telling you, this formalism is telling you is that given that this is fixed, you somehow do this integral and calculate this 1 by z in terms of the number of particles per unit volume, and then go ahead and plug that in here, and that will tell you the energy density. It is a lot of work, but unfortunately you have to do that work, because this formalism comes out immediately and easily only in this language where I allow everything to exchange, that is, I allow energy to fluctuate and the number of particles to fluctuate. So, things become very easy in this case. So, that is the reason why I have temperature, because energy is allowed to fluctuate. I trade energy with temperature, and I allow number of particles to fluctuate. So, I trade the number of particles with chemical potential. So, now if I want to revert back to energy and number of particles, I have to work in the sense of the most probable values. Okay, so with that long preamble, let me get back to where I was, and that is here. So, as a result, so keeping in mind what I just told you, that I really do not care about writing my answers for my energy in terms of the chemical potential. After all, what is Z? Z is e raised to beta mu, and mu is the chemical potential. Maybe I do not care about this. So, what I should be doing is rewriting my Z in terms of things I do care about, which is the density of particles. And it so happens that this expression is simple enough that it allows me to invert it. So, remember that when Z is small, I can throw away this, all these other terms, and then the inversion becomes straightforward, and it is a linear relationship. And so, recall that Z is small implies, so if at fixed density, if I fix my density, if I fix the number of particles and my volume and so on, so on an average, that is. So, if I fix it, then the only way I can fiddle around with Z, I mean, if I have to make Z smaller and smaller in order for this scheme to become more and more accurate, the only way I can fiddle around with this is by making C0. By the way, C0 has dimensions of length, and it is sometimes called the thermal wavelength. So, this has a name, this is called thermal wavelength, and in fact, this is not the standard notation for thermal wavelength. The standard notation is actually lambda T, because remember it depends on beta, which is inverse temperature. So, there is a standard notation which I have been for some reason unwilling to use, but you see many books refer to it as lambda subscript capital T, that is my C0. So, that is called thermal wavelength. So, the thermal wavelength is inversely proportional to the square root of the temperature of the system. So, because it is inversely related to temperature, Z is cube of that. So, it's so Z becomes smaller and smaller as the temperature of the system becomes larger and larger. So, this is basically the semi-classical limit. So, if you remember, I told you earlier that three ways of thinking about the classical limit is either you make h Planck's constant go to 0, keeping everything else fixed, or you make the mass of each constituent go to infinity, keeping everything else fixed. The third alternative is you keep everything else fixed and make the temperature go to infinity. So, either of these possibilities allow you to study the classical limit of a quantum gas. Alright, so that is precisely what we are doing now. The small z expansion is just code word for classical expansion. So, keeping that in mind, I can go ahead and substitute this formula for z in terms of rho, and I get this kind of an expansion, a semi-classical expansion for the energy density of a quantum Fermi gas at high temperatures. So, remember, this is semi-classical is high temperatures. So, high temperatures, the leading contribution to the energy is the classical ideal gas result, which is U is 3 halves n T. And then you also have quantum corrections. So, notice that the Planck's constant appears prominently in the numerator. So, it is inviting you to make that tend to 0 and get back your classical result. So, if you make Planck's constant go to 0, you get back your classical result, which is total energy is 3 halves n T. So, same here for equation of state. So, the leading contribution is the classical equation of state, which is P V equals n T, and then you can either choose to make Planck's constant go to 0, or you can choose to make the temperature go to infinity, which is the same thing, or you can make the mass go to infinity. So, you see all these possibilities are there for you to stare at explicitly. So, you can recover the classical equation of state using either of these three methods. So, you either make h tends to 0, or you make m tends to infinity, or you make t tends to infinity. So, all these three are equivalent and they all make this thing go to 0, and you get back your classical equation of state. So, but then if you choose not to do that, what you are essentially calculating is the quantum corrections to the classical equation of state and classical energy of a gas. So, the quantum corrections also have hidden in them information about the nature of the underlying statistics or the quantum nature of the particles. So, if it's fermions, only if it's fermions it has this particular form. If it's not fermions, if it's bosons, this formula is going to look very different. I mean, it's going to look the same here, but then it's going to look different there. Okay. So, now let's get to the more interesting problem of the large Z expansion. So, I told you the small Z expansion is nothing but the semi-classical expansion. So, you get back something close to the classical ideal gas results. So, now the reverse is what is known as the large Z expansion or the ultra quantum expansion. So, in the ultra quantum expansion you are actually making the temperature go to 0 instead of go to infinity. So, it is the other extreme limit. So, in order to do this, what we have to do is that I am going to reparameterize my integration variable. Remember, there was some r which was dimensionless. I am going to rewrite in terms of another dimensionless quantity called xi. Okay, so, I am going to redefine r to be this. The advantage of doing this is I can explicitly extract the temperature dependence outside, and then finally, I end up with an integral that only depends on some numerical values n. So, remember this n was either 0, well n was 0. So, n was 0 if I wanted to calculate rho, and n was 1 if I wanted to calculate energy density. Okay, so, I am going to use this now, and so remember when z is very large. So, when z is very large, so here is z there. So, when z is very large, then most of the contribution comes when xi minus 1 is negative. So, when see if xi minus 1 is positive, then z to the power positive is very large, and that very large is in the denominator. So, it is going to suppress the whole thing. However, if xi minus 1 is less than 0, so it is going to be z raised to something less than 0, and if z is very large, that whole quantity is going to become very small, and that is going to tend to 0, and so the dominant term will be 1, and so you get an answer which is not vanishingly small. Well, what I can first do is that given this the fact that there is a natural, the interval between 0 to infinity can be naturally split up into interval from 0 to 1 and from 1 to infinity. So, from 0 to 1 I can rewrite it like this. So, I will rewrite it like, so this is a mathematical identity. I have just rewritten in terms of just split it up from 0 to 1 and from 1 to infinity. Okay, so, this is what you will have to take my word for it. This is how it looks like. So, now I can now make expansions that in the last two integrals it says that the dominant contribution comes from the region near xi equal to 1, and why is that? Because see if z is, since z is much larger than 1 always. So, if z is much larger than 1, so recall that here in this integration limit xi is always between 0 and 1. So, it is less than 1. So, if it is less than 1, this exponent is positive. So, as a result this whole thing gets suppressed. So, the only way it does not get suppressed is when xi is close to 1. So, if xi is close to 1, this becomes close to 0, and so somehow this thing will still survive when xi is close to 1. So, this integral will survive, will contribute dominantly only in regions where xi is near 1. So, as it goes from 0, it is like the integrand, the integration contributes negligibly from 0 all the way up to something close to 1. So, from somewhere from 1 minus epsilon to 1, then only in this region it sort of contributes. In all other regions it kind of does not contribute. So, I am going to explicitly make use of this idea. Here also you can see that because z is much larger than 1 always in this example, remember I am taking the other extreme limit. I have already studied the z small limit. So, I am now taking the z large limit. So, the z large limit, So, again because xi is now larger than 1 in this part of the integration. So, this whole thing is going to be again suppressed unless xi is again close to 1. So, in this integration, when I integrate from 1 to infinity, I have to be, I can get away by integrating it from 1 to some 1 plus epsilon. I do not have to go all the way up to infinity because it is not going to contribute much. So, I am going to make use of this, and I am going to rewrite because I can get away with this like this. So, I can rewrite in terms of, so xi is always close to 1. So, I can write it as 1 plus xi dash, and now notice that xi dash. So, I have split it up into this one, this integration. So, I have split it up into the integration, not split it up, rewritten it in terms of xi dash. So, that is what I have done here. So, I have rewritten in terms of xi dash. So, now notice that because this integrand is substantial only when xi dash is close to 0. So, therefore, when xi is close to 1. So, I do not care what this is, I mean it might as well be minus infinity. It is not going to make any difference, as I told you, most of the integration is going to contribute for xi dash close to 0. So, it does not matter whether I call this minus 1 or call this minus 2 or minus 3, it is not going to contribute much. I mean it is not going to affect my answers that much. So, I am going to be bold and make it all the way to minus infinity, because I know that it is not, in fact it is going to contribute less and less as it becomes more and more negative. So, I might as well do that. So, if I do that, then I can use my expansion. So, remember this is I can use my binomial type of expansion and rewrite it like this. So, that is the story for this integration, the first term here, which I have called I1, I have called this I1. So, now I can do the same thing for this integration, which I am going to call I2. So, the I2 is similarly I am going to write it like this. So, now notice that in case of I1 xi dash was close to 0 but negative, but in the case of I2 xi dash is close to 0 but positive. So, here I have to go from 0. Yeah, so here I am in a happy position, this is already infinity. So, I might as well go to infinity. So, then I can go ahead and do the same type of expansion, and this is xi is 1 plus xi dash, and then I expand and I get this. So, when I do this integration, I finally end up with these results, explicit results for I1 and I2. They look pretty ugly, but that is fine. I am going to be able to use them now. So, I am going to substitute that back in. So, remember that once I get my I1 and I2, I put them back here, because this was I1, this was I2, and I put them back there, and I get this expression. And then when I simplify it, these two terms cancel out. Okay. So, these two terms cancel out, and I end up getting this. So, the leading contribution is this, and the next leading contribution is this. It's the next leading because remember that I am doing a large Z expansion. So, this is the same thing here, same thing there, but then there is a log Z squared, the denominator. So, this is less important compared to this. So, now remember that this is what UV was as usual, okay, in terms of the thermal wavelength. So, this was UV, which is the energy per unit volume, and this was the number per unit volume. So, as usual, I told you that there is an annoying feature which is common to all these approaches that I have discussed so far, and that is that instead of expressing everything in terms of energy density, it is expressing everything in terms of chemical potential, which I do not care about. So, Z is e raised to beta mu, and mu is chemical potential, I do not care too much about it. So, I have to make this uncomfortable but necessary calculation, or I have to perform this step where I convert my chemical potential back in terms of the number of particles per unit volume. So, I have to use this as a kind of dictionary where I translate the chemical potential language back into the number density language. So, unfortunately, it has to be done, and it has to be done on a case by case basis, because for fermions the details are different, and for bosons the details are very different. So, for fermions it so happens that at absolute 0, the chemical potential actually freezes to a certain value which I have called mu f. So, remember that large Z expansion is same as low temperature expansion for reasons that are obvious, because large Z means e raised to beta mu is large, and you can think of mu as something fixed and then make beta large. Beta large is same as temperature is small. So, if you believe my assertion, of course, let us make this assertion and then convince ourselves that it is correct, and namely that at large Z expansion or low temperature expansion, I am entitled to write the chemical potential as something mu f, which is the chemical potential at 0 temperature times term, which is going to be small as temperature tends to 0. Okay, so I am going to also introduce a new quantity called Kf, which is basically called the Fermi wave number. So, the Fermi wave number is defined as the chemical potential at absolute 0 when it is expressed in terms of Pf squared by 2m, and where Pf is the Fermi momentum, which is defined as h bar times the Fermi wave number. So, this is nothing but Pf squared by 2m. So, if I rewrite my chemical potential at 0 temperature in terms of this, that is what it is. So, so I can re-express my density in terms of Kf. Now that I have been able to do this, I can go back and rewrite this formula. So, this formula, if I rewrite in terms of Kf and I plug this back into this formula here. So, I put n equal to 0 and I put this in here, I get this rather ugly looking expression which I have to solve. Okay. So, keep in mind that in this case x is really small, and because of that I have expanded mu to the 3/2. I have written as, in fact, I got something like this, which I have approximated as 1 plus 3/2 x and so on. That is what I have done here. Okay. So, other than that I have not done anything else. So, now if you stare at this, you will see that after simplification I will be able to write down an answer for x. You see this term. So, basically what is going to happen is that this term will see, because when beta is very large, so low temperatures, okay. So, there is a beta to the power plus 3 by 2 sitting here. So, that is very important. There is a beta to the power minus 1/2. So, that is less important. But then this will one can suspect there will be 1 by beta sitting all over the place in x also. X depends on beta. So, there will be 1 by beta to the power something, some positive number. So, this is also because x is small at low temperatures. So, this term is going to be as small as this term. So, the term that is most important is this one, and by construction this term is the same as this one. When all put together, everything put together, this term and this everything put together is this. So, that is how I have constructed it. So, as a result I can equate the rest of it to 0. When I cancel out the 0th order term, the first order terms also have to cancel out. So, that will tell me the relation between x and the rest of it. So, the answer comes out to be this. So, instead of rambling on and on, I think what you should do is not allow me to ramble on and on. What you should do is pause this video and go ahead and verify all these steps on your own right now, and just pause the video. Just go ahead and take a piece of paper or several pieces of paper and a pen, and work out all the steps until you are sure about what you are doing and what I was saying. Make sure that what I was saying was right, and it is right, but make sure it is right. So, convince yourself that it is right. Okay. So, I am going to allow you to do that, and now let me stop here, because I am going to continue discussing how to get the equation of state and the energy density of an ideal Fermi gas explicitly in terms of temperature by completing this calculation. And later on what we will do is we will learn how to repeat this calculation for an ideal Bose gas. And once we do that, we will be in a position to consolidate all these results we have obtained in one big slide, and we will be able to stare at them. So, remember, we have succeeded in studying the classical ideal gas, which was really simple, but then we also succeeded in studying the quantum Fermi gas both at low and high temperatures, and later on we will study the quantum ideal Bose gas at low and high temperatures also, and then we will be able to put down all these results in one slide and stare at them. And when we stare at them, we will notice a pattern, and that pattern will enable us to introduce what is known as a virial expansion of the equation of state. So, let us get to that gradually. So, we are going to study that and that is very interesting and very useful. Okay, so I am going to stop here. Thank you.